lot of you know him. He's been around here for a while. Chuckles there. He's currently with the Hawaii Department of Health. He's working with the source water protection plan, where he's had around 18 years experience, certainly at least in groundwater modeling projects. A lot of work involving contamination systems, involved groundwater modeling and risk assessments. He's been a consultant geologist for a component of the Red Hill Fuel Storage Facility, not supposed to, and the decommissioned Air Force fuel tanks out in central Oahu. He's well known for his work on the SWAP, groundwater source assessment programs in throughout the Hawaiian Islands. Important publications. First one came out about Oahu, and the second one concerning all the rest of the Hawaiian Islands. And on-site disposal systems, we'll be talking about that today in some detail. And most recently, working in our group, my personal experience is working with Bob is in the Lahaina wastewater injection tracer project, making hydraulic connections. I think he's going to touch on that today as well. It's a big multi-million-dollar lawsuits involved in all this stuff. So we have, Anyway, today's talk is wastewater meets groundwater and beyond.
Well, thank you, Craig. Although I work at the Department of Health, they kind of think I work at the university because I spend a lot of time up here. So everything we say here is basically from work at both places and from that perspective of both the academic and the regulatory approach. But it does not necessarily reflect any policies of the University of Hawaii. And that will make my friend in the Attorney General's office happy that I said that. Well, the title of the talk was Wastewater Meets Groundwater, but really why are we concerned if groundwater is contaminated? It's down there a couple of 100 feet, it's not hurting anybody, nobody really should care. It's when groundwater is no longer groundwater that we start caring because all that groundwater that is not extracted by wells, and if it's extracted by a well, it's no longer groundwater, will discharge either to streams or to the coastline. Now we start caring because those are things that are valuable to us. So in this talk, we'll give an overview of wastewater in Hawaii, the methods of dispensing and usually disposal of wastewater, an overview of some of the scientific investigations dealing with wastewater issues, and some of the legalities, and also what we're currently doing at the Department of Health in dealing with wastewater issues. Well, currently we generate about 200 million gallons per day of wastewater, and we dispense with it about 4 basic methods. Deep ocean outfalls, put in pipes into the out a mile offshore, and then let it disperse into the marine environment. Doesn't really affect groundwater. Next method is injection, direct injection into the groundwater, so definitely that affects groundwater. Since groundwater doesn't stay groundwater, it will also affect the marine environment. On-site sewage disposal, where we dispose of the wastewater at the same parcel where it is generated. Again, it's going to leach down to groundwater, so it will affect groundwater. Groundwater discharges, so it's going to affect the marine environment. And lastly, reuse, recycling the wastewater. In land application, you usually try to apply it at the consumptive rate, but regardless, at some point, you're going to get recharged to the aquifer. And potentially some of those constituents in the recycled water will make it to the groundwater, potentially eventually to the marine environment. So potential for impact there. But going back to reuse, it is, we call it wastewater, but is it wastewater, or potentially is it an underutilized resource? So let's look at Oahu. Oahu, we have about 76 permitted treatment plants. Most are small. They serve like condominium, a small shopping center, etc. About half of them inject their wastewater directly into the ground. And I looked at about, and mapped here, about 15 of what I call the major wastewater treatment plants, and looked at how they dispensed or disposed of their wastewater. 4 inject directly into the groundwater. 7 discharged to deep ocean outfalls, which is shown by this barrel with the whatever it is pouring out of it. 2 inject, or actually discharged to surface waters, and 2, their primary source or method of dealing with the wastewater is to recycle it. But we also have dispersed around the island a whole bunch of what we call on-site sewage disposal systems. Estimated to be about 14,000, and these means that we generate the wastewater on site, dispose of it on site, usually through septic system or a cesspool. And as the numbers show here, primarily through cesspools. Of the 14,000 OSDS, 11,000 are estimated to be cesspools, where that wastewater receives no treatment prior to being released to the environment. And finally, we take about 12.5 million gallons of this wastewater and process it and send it out for reuse. Do that at 7 plants on Oahu are capable of recycling water: Honolulu, Schofield and Marine Corps Air Station, Wahiawa, Waiaga, and Laie and Turtle Bay. So what are the groundwater management issues? Well, first off, groundwater and coastal water, and I should add to that surface water, should be used as a single continuum. Groundwater not extracted by wells or discharging to streams winds up in the ocean. And the considerations are these point sources of pollution, i.e. as an injection well, or non-point source? An example would be on-site sewage disposal or reuse. And finally, the contaminant flux and contaminant mitigation. Through wastewater treatment, we mitigate it by design, but also it should not be ignored that a lot of incidental contamination mitigation occurs. That after we release it to the environment, the process does not stop. So relative magnitudes for these various methods of getting rid of wastewater. By far, most of our wastewater is discharged to deep ocean outfalls. Good for groundwater, and maybe not even that bad for the marine environment because a large pool to disperse it in. Now, if we look at things that potentially affect groundwater, we have the surface water discharges. And the reason that was included is because all this actually gets distributed into an irrigation system and potentially to the groundwater. Injection, definitely a connection with groundwater. On-site sewage disposal, what gets released to our cesspool will migrate down to groundwater, so definite groundwater impact, and potentially from reuse water. We're going to with about a total of about 225 million gallons per day of wastewater generated, and about half of that could potentially impact groundwater. So we'll talk about each of these in order: the discharge of surface water and injection, with a focus on the Lahaina groundwater traces study, including recent data that has been made available and an overview of some of the regulatory and legal issues, and on-site sewage disposal systems, various past and ongoing studies, and an update of what's being done. And if there's time, a little bit on reuse. So we have 2 plants here in north central Oahu that send their wastewater to surface water bodies. Wahiawa discharges its water to Lake Wilson. Lake Wilson feeds the Wahiawa ditch, which feeds the North Oahu irrigation system. Schofield Barracks, actually this is located at Whittier Army Airfield, also treats water to recycle standards and sends it directly to the Wahiawa ditch. Now here's where it gets kind of confusing, the possible impact of groundwater. definitely this in the light blue is water that has a wastewater component, recycled wastewater component. And areas here most undoubtedly receive irrigation water with a wastewater component. But Lake Wilson and the Wahiawa Ditch is not the only source of irrigation water for the North Oahu irrigation system. We also have the Halemanu Reservoir and the Opai'ula ditch system. And there's a lot of interconnection. So most certainly in this area here we get some wastewater contribution, less so as you go north in that north central Oahu plain area. Wastewater injection, direct input of wastewater to groundwater. Reviewed the underground injection control permits. In order to inject wastewater, you have to get a permit called an underground injection control permit. Broke it down into 7 different categories. Military had the lowest amount that was injected, about 1,500 gallons per day. And this is because they sent most of their wastewater to deep ocean outfalls. Also included, but not very much in volume, would be recreational, i.e. beach parks, boat harbors, small amount, about 32,000 gallons per day. Commercial, like Haleiwa Shopping Center, and establishments like that, about 153,000 gallons per day. Small government, this would be hospitals, nonprofits, a little bit more, 160,000 gallons per day. Now, when we get to resorts, we're starting to get into bigger numbers. Resorts injected or permitted to inject about 1.6 million gallons per day. Residential, this would be condominiums, about 2.5 million gallons per day. But municipal, the large wastewater treatment plants operated by the counties, are permitted to inject about 27 million gallons per day of treated wastewater into the groundwater. Which brings us to the Lahaina groundwater tracer study. Wastewater has been injected near Lahaina for about the last 40 years. And it was injected, and there were a lot of people pondered, okay, we inject this wastewater, where does it go? We inject it into the saltwater zone. We're hoping that it gets trapped down here in the bedding of the lava flows and gets discharged to the ocean deep water and quite a ways offshore. But maybe not. So in 2011, the University of Hawaii, the County of Maui, EPA, Department of Health, and the Army Corps of Engineers all teamed to answer that question. We did that with the groundwater tracer test. The primary goal of the groundwater tracer test was to determine whether or not there was a hydraulic connection between the wastewater injection wells that are about 500 meters from the coast and the coastal waters. Secondary goal was to characterize the nutrient and wastewater flux to the coastal waters. So, used several methods. Primary method, well, we did a tracer test, but also did a lot of chemistry. Characterized the nutrient chemistry of the upland waters, the wastewater, and the coastal waters, along with the geochemistry, stable isotopes, and the radioisotopes. And also did another very interesting survey, and that was a sea surface temperature survey from an aircraft late at night to look at any temperature anomalies in the surface of the nearshore waters. Though, of course, this was my favorite, the tracer test. We, in about, it was July 28th of 2011, took about 350 pounds of fluorescein, dissolved it in about 1,700 gallons of water, and over a period of 20 hours, added that to the primary injection wells, which were injection wells 3 and 4. 2 weeks later, we did a redo, but we did another dye, rhodamine dye, this time 180 pounds of that dye, put it into well 2, and we never saw it again. there had been seep locations, submarine spring locations that had been identified during a previous survey. These were sampled continuously from before we did the dye injection and actually still ongoing. We did our tracer test, started sampling about 3 times a day. After a couple of weeks, backed off to twice a day, and then kept decreasing the frequency till now we're doing it about once every other month. And in spite of what this picture may show, we did actually get some dye down the wells. Actually, most of the dye went down the wells. So what do we get from a tracer test? We get a neat graph called the breakthrough curve. Breakthrough curve is nothing more than a time series graph of the concentration of the solute of interest, in this case, the difluorescein, versus time. So this graph starts right here, where we add the dye on July 28, 2011, and continues to the present. And we get a lot of good information from this. One, we verify that there is a hydraulic connection between the injection wells and the nearshore waters. But we also get a velocity, the travel time of from those injection wells to the nearshore waters. First arrival occurred about 3 months after injection. It peaked, concentration peaked about 300 days after the dye was added. Average travel time about 350, basically about a year. But we had a very long and slow declining limb to the breakthrough curve. Now this average time of travel is a little bit different than what we stated in the report. In the report we used a term, and if I recall right, it was the mean residence time, which is defined as the center of mass of the area underneath the curve. And you say that, people go, what the heck are you talking about? So redefine that to say that the average travel time is defined by the time it takes 50% of the dye mass represented by this curve to pass from into the ocean, past the sampling point into the ocean. So that was about a year, and that equates to an average groundwater velocity of about 2 meters per day. So we have a very long declining limb, and so we still have detectable dye concentrations, and they will remain detectable for about 6 to 7 years past the time of dye injection. So we did a 20-hour injection, we wind up with a 7-year breakthrough curve. The other important thing from a modeler's perspective, so for me and Ali, is that we were able to estimate what's called a dispersivity value. This, of course, is a plume that is much longer than the amount of time that was injected, and that's due to dispersion of the plume as it moves through the subsurface. So for modeling, you apply a numerical value called dispersivity. And so based on the ascending limb of the breakthrough curve, we estimated a dispersivity of about 25 meters. Probably one of the few times that that parameter has been directly measured in Hawaii aquifers. But tracer test is not the only thing we did. We did a stable isotope chemistry. Actually, this was actually done before, nitrogen-15. Turns out that wastewater is enriched in nitrogen-15 relative to nitrogen-14. Becomes a good wastewater tracer indicator. The other thing was that Craig's group did a thermal infrared imaging flight along the Maui coastline late at night to look for any thermal anomalies, and we got one. And shown in here is a green graph, and this is normalized to the maximum value of the sea surface temperature. See a baseline, 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 then a sharp increase, very high sea surface temperature, and then it decreases. This peak represents values that are 1 degree centigrade or greater above normal sea surface temperature. Plotted on this same thing is our cross-section of the dye plume. And there's very good correlation between all three parameters, at least at this point here, indicating that they all are valid wastewater tracers. We use the dye to validate the other methods, even though they were enormously high in this area. The reason we say that is that you can make excuses for elevated sea surface temperatures, geothermal plume underneath the sea surface, other things that could cause an elevated nitrogen 15, but the only place that fluorescein was added into wells 3 and 4. So anything that shows elevated concentrations of fluorescein means that injectate from wells 3 and 4 are in fact discharging near the shoreline. And this graph right here shows the integrated dye plume extended to about 100 meters offshore. So again, the correlation between the sea surface temperature, delta N15, and the dye validates each as a wastewater tracer. So our study ended in January or December of 2012, but because we did confirm that hydraulic connection between the injection wells and the coast, the Clean Water Branch of the Department of Health took over and started sampling these submarine springs that had been identified, looking primarily at the nutrient concentrations. And it was very interesting. From about January of 2012 until about March of 2013, had very low levels of nitrogen, about equal to, quote, be the clean water standard, 150 micrograms per liter. So that's good. When we were doing our work, and also work done by the botany department before, actually measured the delta N15. And losing my place here. And the values along the coastline went from about 4 to about 40 parts per thousand delta N15. Well, if we look at wastewater, wastewater has a delta N15 of about 30 parts per thousand. At the seeps themselves, there was a ratio of N15 to N14 of about 90 parts per thousand, much higher than even wastewater. Correlate that with the very low nitrogen concentrations, and it's a very strong indication that denitrification is occurring, which is good. But starting here in about March of 2013, nitrogen starts increasing, and that continues to be at a little bit below or near the concentration of nitrogen in the injected. That's not good. So what happened? In October of 2011, because we had seen a connection between the injection wells and the nearshore waters, Maui County was directed to go to full disinfection. The quickest method to do that is chlorine. Chlorine is good at killing bacteria. Unfortunately, bacteria are also the process that converts nitrate to nitrogen gas, denitrifying the wastewater before it gets discharged into the environment. And that's the leading hypothesis. Bigger year travel time, and that reactive transport, this being a chemical reaction, is a little bit slower. The timing is about right. Started the full chlorination in October of 2011. See effect about this short of a year and a half later at the seeps of increasing nitrogen. That chlorination continued as a primary method of disinfection until about May of 2014, but some chlorine disinfection continued till about August of 2014. So now, we're about a year past that. Hopefully we will start seeing these nitrogen concentrations decrease, which will kind of validate the hypothesis that chlorine disinfection disrupted the denitrification process. So what else can we do? Another neat thing that was done was a coastal radon survey. Radon is a radioactive gas. Most common isotope has a short half-life, about 2.8 days. key point is that there's almost no radon in seawater because there's no radium to decay the radon. Groundwater flows through the rock matrix. We have radium there, some of it gets dissolved, but regardless, you will pick up radon in the groundwater. So any radon anomalies in the seawater almost certainly indicate the discharge of groundwater. So Henrietta and her group did a coastal survey of the radon activity. If you apply some corrections, some equations, you can convert that radon activity to the magnitude of submarine groundwater discharge. You apply a couple more corrections and you can back out the recirculated seawater and say, well, this is the amount of freshwater discharge. Back it out one step more and apply the dye, and you can actually say, well, this much is probably wastewater. So we did those steps. And here on the left-hand side is a color graph of the magnitude of submarine groundwater discharge in units of meters cubed per meter squared per day. So specific discharge. Most of the SGD occurs in the northern part of the, and this is mapped to the identified plume of the tracer dye. Most of the discharge occurs up here in the north. Much lower amounts as we go to the south. But we integrate that submarine groundwater discharge with the dye, and then everything shifts a little bit south. We still have most of the wastewater discharge here in the northern part, but we still have significant amounts as you move south. But the key point is that we can use that to calculate some other important parameters from an ecological point of view. What is the flux of nutrients or contaminants to the coastal waters? Then, that's several series of calculations done. First, back in the early 90s, there was concern with algae blooms in West Maui. So Tetra Tech was contracted to do a nutrient analysis of the flux of nutrients to the shoreline. And they, of course, looked at one of the bigger producers of nutrients, and that would be the Lahaina Wastewater Treatment Facility. Back then, that was not doing as advanced treatment as they're doing now, and the injected concentrations of nitrogen and phosphorus were actually very high. And it was also assumed that there would be no incidental remediation of the wastewater as it moved into the marine environment. So we got very high estimates of nutrient discharge, 150,000 pounds per year of nitrogen, about 130,000 pounds per year of phosphorus. USGS in 2012 went and actually did some direct measurements. They measured the chemistry of the discharge at the springs, and also using radon, estimated submarine groundwater discharge. So much lower concentrations of both phosphorus and nitrogen, and also much lower submarine groundwater discharge. They assumed, they extrapolated their calculations, assumed a plume width of 50 meters. So now we have some really low numbers, about 1,500 pounds per day, or pounds per year of nitrogen, about 800 pounds per year of phosphorus. We did our study and sampled the submarine springs and got a little bit higher, and also using radon analysis came out with a higher flux, so we come up with significantly higher numbers, which means only because we had a more comprehensive data set. So about 7,500 pounds per year of nitrogen and about 3,000 pounds per year of phosphorus. Now, if you take the long-term monitoring data from the Department of Health prior to March of 2013, now the numbers go back down significantly. We had a concentration of about 0.15 milligrams per liter of nitrogen discharging, about 0.4 milligrams per liter